Hello and welcome back. In the previous video, I we talked about this three-story building, and I showed you how to write the transition function, measurement function, and use unscented Kalman filter to estimate the hidden states and identify the parameters. In this presentation, I'm gonna go one step forward and ask you, what if there is a damage in a specific floor of this building? For example, the building is experiencing earthquake and one of the floors is damaged. How can we The first step is to be able to detect the damage. Do we have a damage or not? Then once we are looking into the vibration signal, we need to be able to detect the damage. Okay, do we have damage or not? Then the second step, second thing we need to answer is which floor is damaged. We need to localize the damage. And once we localize the damage, we need to quantify the level of the damage. Why? Because quantification of the level of the damage can help us to make risk-informed decision. Is it the right time to repair the building? Is it, for example, for a mechanical system, a vertical access machine? Is it the right time to replace the bearing? Or if it is not, can we anticipate the right time to replace the bearing or not? Then this is a damage identification problem, which helps us to make risk-informed decisions for the mechanical or structural system we are working with. For example, assume that I have the free vibration response of a specific floor of this building. You see in the left side. I calculated the FRF of this free vibration response, and you see the first three natural frequencies is 3 hertz, 12.9, and 36 hertz. What I do, I change the stiffness of the one of the floors. For example, I change it 20%. From the 50,000, I change it, I don't know, to 40K. Okay. Then I measure the free vibration and I plot the FRF as well. You see in the new case, for the new scenario, the natural frequency changed from 3 to 2.8. The second natural frequency changed to 11.3, and the third one is still 36. Okay. Then right now, I'm just looking into the data. I recorded the vibration response, acceleration of the vibration, the free vibration response. I translated the vibration into the frequency domain, and I looked at the peaks, the natural frequencies. You see, if I change the stiffness 20%, the first natural frequency changed from 3 to 2.8. What's happening here? We have a change in the natural frequency. It means the dynamic of system, the nature of the system is the physical property, the properties of the system is changing, the stiffness value, because this is a simulation study and I changed the stiffness value. But the natural frequency is changing less than 10%. What's happening here? It means you are able to detect the damage, or because you see the first and the second natural frequency are changing, but the third one is not changing. Maybe you are able to localize the level of the damage. For example, the change of stiffness in the first floor or second floor, but you are not able to quantify the level of the damage because the change of stiffness is 20%, but the change of natural frequency is less than 10%. Then there is not a linear relationship to if you look at only into the natural frequency and if you want to quantify the level of damage, then you need something else. Then I talked about this concept here to show you how Kalman filter can be useful to quantify the level of damage. And if you just use traditional frequency domain or wavelet domain technique, techniques, you are able to detect the damage, but you are not able to quantify the level of the damage. Now, as I said, you are not able to quantify the level of damage because you have 6% change in the natural frequency, while you have more than 20. You change the stiffness 20%. This is the problem. We have a three-story building, and we impose damage to the first floor of this building. This is the K. For the simulation, for example, we excite the building with, once we are exciting the building with this earthquake, with this earthquake story, at time 10, we reduce the stiffness from 50K to 45K. And at time 20, again, we reduce the stiffness to 40K. Then the problem here is the problem statement here is to see if the standard unscented Kalman filter we defined and developed everything in the previous presentation can be used to quantify the level of the damage or not. In another word, is the unscented Kalman filter able to track the rate of change or not? Let's see. Yeah, what I did, I implemented the unscented Kalman filter here. Okay, again, similar to the previous one, I assumed I only measure the acceleration of the vibration in the first and third floors, and the acceleration of the vibration in the second floor is missing. At the beginning, unscented Kalman filter was able to catch the ground truth, which is 50K. And after that, once I change the stiffness and continue the same unscented Kalman filter algorithm, you see, the unscented Kalman filter is not able to quantify the level of the change it doesn't work anymore. Why such a thing happened? This is the question we need to answer. And this is one of the things that the traditional unscented Kalman filter is not, is a bit lazy. In another word, for any type of Kalman filter, we say the Kalman filter is a lazy algorithm. It's not able to catch the change. We need to modify the algorithm a bit to be able to catch the change. Okay, if we use unscented Kalman filter here, then what we expect to see is something like this. At the beginning, we are able to get the ground truth. Once the filter um, catch, we change the stiffness, we expect the filter go and catch the change and be able to quantify the level of the damage for us. Why? The standard Kalman filter is not able to do that. Let me tell you what I did here in a simple word that you see such a result. In a simple word, in any type of Kalman filtering technique, you remember that for any type of Kalman filter, for example, let me write it down here. What we had, as I said, the main equation for any type of Kalman filter was, for example, the update for the mean was x was equal to x hat, which was the mean prediction, the mean of the state prediction, plus k dot times y minus y hat. Yes, this is the famous equation and the main equation of the Kalman, which update the state prediction based on the weighted difference of the predicted output versus the sensor measure. And the next equation we have was the P, the covariance of the updated state, which was P of XX for unscented Kalman filter minus K, which is Kalman gain, PYY K transpose. Yes? Then this is update of mean. This is update of covariance. The trick I used to show you that how Kalman filter could be strong or capable to quantify the level of the change and to find a solution for is this. At time 10, because that was a simulation study, and I knew that the change of stiffness is happening at time 10 and 20. What I did, I said if time is equal to 10, reset the P. and here as well. You see, in the previous plot I was showing you here, I was not changing the p at all. It was I defined my initial p at time equal to 0, and I let the Kalman filter go forward. But here in this case, once we have a change in the stiffness, I reset the p, and here also I reset the p. What's happening here? Once we reset the p, we push Kalman filter to go and search more. You see, P is kind of a fuel here. The thing that the thing that stimulate, push the Kalman filter, go search, go search. Then, in another word, if we have a change in the model, and first of all, we need to detect the change. We need to define a trigger point, a criteria to be able to detect the change. And once we detect the change, we we stimulate the Kalman filter and tell it, okay, reset your P or do whatever you want, and use any technique you want to go and search again. Don't rely on the previous predictions and sleep on it. You see what I'm saying? Then here, my point is, once we have a change, the point is to reset the P, to push the Kalman filter to go and search. Um, Okay, now then to be able to change to now assume you are on a real problem, you're solving a real problem. You don't know where the damage happens, when the damage happens. Then you don't know the right time to reset the P. Then you need to be able to find a method or an algorithm or define a criteria to be able to change the p or increase the p value, because once you increase the p value, you tell the Kalman filter to explore in another value in a wider range and try new values and see if it reduces the loss function of the Kalman filter or not. Then for this case, we need to go and look at the P. Okay. Technically, we need to increase the P. Okay. To increase the P, we need to look at this PXX, which is the P hat XX plus Q. And for this K, we cannot change it directly. Then we have this Q here, which we can play with. Another thing is this PYY, which is PYY hat plus R. Then, and this is another things we can play here. And this is another things that we can play. I'm gonna write it here. Okay. Then, based on what I said, if there is a change in the system, we need to push the Kalman filter to go and catch the change. Uh, Technically, as I said, we have to increase the P. The one way to increase the P is if we know the right time of the damage, okay, we reset the P. But in a real case, we don't know that. What we do, we look at the equation. In this equation, P hat XX is coming from the predicted state. We cannot change it that much. But if we define something to be able to change the Q and R here, technically we are changing we can play with these two parameters and increase the P. Okay, that's bring us to the next point I wanted to talk about, and that's adaptive R and Q. So far in every problem we were solving, I was assuming Q and R are fixed. And I never talked about it in detail. And for every case study I assumed, we know how to find the optimal Q1R which are fixed. And then in the next video, I'm gonna show you how to write the Q modeling error and measurement error in adaptive ways, and and use it to be able to quantify the level of the damage for any dynamical system. See you in the next video.